Alright, this is Mark Anderson from Kellogg Community College, and I am going to be looking at solving for x with exponents and logarithms. So here's the principle of exponential equality. If I have log base b of b raised to the x power, that's going to give me x. Because due to an earlier property, the power product, or the power rule of logarithms, this x can be moved to the front, and log base b of b is 1, and 1 times x is x. We're going to be using this rule when we have an exponential problem. Now, what if we have a logarithmic problem? Well, then b raised to the log base b of x is the same thing as x. Again, we can move this to the front and write it as log base b of b times x. Since log base b of b is 1, 1 times x is x. This is if we would have a logarithm and needed to basically solve for x from there. So what I'm about to do is use this first rule, the principle of exponential equality, to get the x by itself. Now you'll notice that the left and the right hand side both have base 3. Well, to basically get rid of the 3, which we're actually kind of not getting rid of it, but to think like the inverse operation, one of the main points of units 1 and 2 in this chapter on logarithms is to teach you that the inverse of the logarithm is the exponential, and the inverse of the exponential is the logarithm. So to get rid of the exponential, we're going to take the log base 3 of both sides. Sorry, that's a little cramped there. So what this means is that log base 3 of 3 is 1. The 2x minus 1 can be moved to the front, and 2x minus 1 times 1 is just 2x minus 1. This x minus 3 can be moved to the front, and that log base 3 of 3 is 1. So 1 times x minus 3 is just x minus 3. So I think what you're seeing here is that some people will just, without trying to think of all the manipulation, just say, oh, the opposite is the exponential is logarithm, and vice versa. And that's satisfactory, but I think you should try for some deeper knowledge here. Subtracting the x from both sides, we're going to get an answer of x minus 1 equals negative 3. Then I'm going to add 1 to both sides, so x is equal to negative 2. So there's my answer for that. Here, again, with both being base 8, I'm going to take the log base 8 of both sides, because anything you do to one side you have to do to the other. This x minus 3 moves to the front, and then 1 times the x minus 3 is just x minus 3. Here I'm going to move this x minus 3x plus 5 to the front, and log base 8 of 8 is just 1, and now we're solving for x. I'm going to subtract x from both sides, moving my x's to the right to make a total of 2x. And I'm going to then move my 5 to the left by subtracting it. So negative 8 is equal to 2x. Dividing both sides by 2, x is equal to negative 4. Moving on to the next two problems here. I notice that my base is 1/2 on the left side, but you'll notice that on the right hand side my base is not 1/2. It's just a whole number 4. So I'm going to take the log of 0.5 to both sides, and you'll note that the log of 0.5 to the 1/2, you can bring the x to the front, and x times 1 is just x. Here on this side we have log of 0.5, 4, so you can use your change of base formula if you can't type that into your calculator, if it doesn't have the log base format under the math key. You can divide log of 4 divided by log of 5, and this is the change of base formula learned in a previous video, to get us an answer of negative 2. Now here, notice that my base is 10. So if I take log base 10, or just the log, because log without any number next to it is just base 10, this x moves to the front, and this gives me x. And then over here, log 10 is just 1. Because log base 10 to get to 10 would take me one stage. In number 5, we're going to use log base 3 on both sides, and that gives me a negative x is equal to log base 3 of 15. So this is going to be log 15 divided by log 3. If I do the division here, I get a decimal, and that decimal is going to be positive 2 and 465 thousandths. the directions up above were to round to the nearest thousandth, or 3 decimal places. Dividing both sides by -1 gives me an answer of -2 and 465 thousandths. Now this last problem here is just a little tricky because you'll notice that the base on the left is 4 and the base on the right is 2. Now we can't actually take different logs on different sides of the problem, so what I'm going to try to do is get everything in log base 2. And I can do that because 4 is the same thing as 2 squared. So if I rewrite the problem as 2 raised to the 2x power, and then 2 raised to the 2x plus 3 power, I can take log base 2 of both sides, and now we'll have some nice simplification. The 2x comes to the front, and 2x times 1 is 2x. The x plus 3 comes to the front, and x plus 3 times 1 is just x plus 3. Subtract x from both sides, so x is equal to positive 3. And there's your answer there. Now, interesting things happen when you see e, which is an exponential number. In fact, e is on your calculator. Look on the left-hand side, below log, above the natural log key, there is a little e, and you can obtain that by hitting the shift button. Now, what we should try to do is get everything over to one side, so I'm going to divide 3 by both sides, and that gives me 9 is equal to e raised to the 2x. Now, to get rid of this e, we have to take the log base e of both sides, but that's just natural log. So if I take the natural log of 9, I get the answer of 2 and 197 thousandths. If I take the natural log of e raised to the 2x, it's the same as the 2x being brought to the front, and the natural log base e to the first power is just 1. So you have 2x here. If you divide both sides by 2, x is equal to 1 and 99 thousandths. And so that would be my answer for the problem. So in the last 7 problems, we have seen the problem start with an exponential. Well, in this case, in problem number 8, it's starting with a logarithm, and not just any logarithm, it's starting with the natural logarithm. So what is the opposite of the natural log? Well, that would be e. So I'm going to now use the principle of logarithmic equality and make e my base of each problem. And so if this is e raised to the natural log of x, I can move the x out to the, I can basically make this the natural log base e times x, and 1 times x is just x, and e to the 4th is going to be my answer, and I can approximate that by typing that in. As soon as you hit second natural log, it will give you a little caret to put where your power in the corner, and that would be 54 and 598 thousandths. So for the next, let's see here, 1, 2, 3, 4, 5, 6 problems, we will look at starting with logarithms, and starting with these logarithms, we are going to use that rule, the principle of logarithmic inequality, to basically solve for x by simplifying the log. Because we need the x by itself, so in this base 5 problem, I'm going to take everything to a base of 5. Through the power of this simplification, everything moves to the front here. Log base 5 of 5 is 1 times x plus 1, which is just x plus 1. And 5 squared is 25. I subtract 1 from both sides. X is equal to 24. Now, I would honestly check your answer. And the reason why you should check your answer is because any logarithm, and I'm going to draw just the base logarithm here, the domain is going to be where x is greater than 0. So sometimes when x is negative, you should check to see if it actually works by plugging it back into the problem. And it actually does, because 24 plus 1 is 25, and in base 5 to get to 25 you need 2 stages, or the exponent of 2. So this answer checks and we're clear. But just check your answer to make sure it works. Let's, using the base of 3, if I put the base of 3 of this, move this to the front, log base 3 of 3 is 1, so 2x minus 1 is equal to 3 to the 3rd power, which is 27. Adding 1 to both sides gives me 28, and x is equal to 14. I should check my answer, though. So 2 times 14 minus 1 is 27. In log base 3 to get to 27, I need the third power, so this answer checks. Now let's look at the next two problems. The next two problems both look very similar. They have x squareds in them and x's, but here we have our log base 4. We're going to now simplify this, and I'm going to move a little bit faster because we know the manipulation now. And on the right-hand side, it's 16. Now, one of the things about a problem like this is that with an x squared and an x, you're either going to use quadratic formula or factoring. So we're going to set this equation equal to 0 by subtracting the 16 from both sides, and then hope that it's factorable. Because we can use the quadratic formula, but look how fast factoring is. X plus 8, x minus 2. If I set these equal to 0, I can solve for x and get my two solutions of -8 and +2. But here's something you should think about. You should ask yourselves, oh my goodness, what if I plug this in and it doesn't actually work? But the good news is it does. I mean, if you try plugging in the 2, you get 2 squared, which is 4, plus 6 times 2, and 6 times 2 is 12, so what you get is 4 plus 12, which is 16, and log base 4 to get to 16 is the second power. But try the -8 and see what happens. Here you get positive 64, and here you get 48 negative, but a 64 and a negative 48 both make 16. Both answers actually work. Now, I know you were a little bit worried that the domain had to be where x is positive, but if you check this out, you'll notice that the -8, if I plug into the problem, makes a positive x, so it works. Now, down here we have a base of 6, so this is going to be x squared minus 5x is equal to 36, because that's 6 squared. Again, a common mistake would be to put 12 here. So x squared minus 5x minus 36 equals 0. Well, let's go and take a look at this. This is going to be x minus 9 and x plus 4. And if I set these equal to 0, I'm going to have an answer of x equals 9. And if I set this equal to 0, I'm going to have an answer of x equals -4. Uh-oh. Does it look like this is going to work here? Let's check. All right. We get 36, and 6 to the second power is 36. And the same thing happens here with -4. If I plug in the -4, I get 16 and then 20, and 16 and 20 make 36, which again work. And oh my goodness, look at that. They both work in this situation. All right, so moving on to my final two problems here. What I'm going to do first is I'm going to take the base 5 of both sides, and that means I'm going to have 3x over x minus 1, because that simplifies to 1 times that, and 5 to the first power is just 5. Now what I would do here is either cross multiply or clear the denominator. So either way, the denominator has to be multiplied by x minus 1. So here I have 3x is equal to 5x minus 5. I subtract the 5x from both sides, and I get 2x negative equals -5. And then I divide both sides by -2. X is equal to 5 halves. And I don't have the calculator function open right now, but if you do this problem and you plug into this situation here of 7.5 right there, because that's 3 times 5 halves, or 15 halves, 7.5, divided by 5 halves minus 1, or 3 halves, or 1.5, 7.5 divided by 1.5 is 5. So log base 5 of 5 is 1. So the answer checks out. So for our final problem here, I know one of the common mistakes is that we want to just base 7 all of these things, but you actually can't do that. Let me explain why. In this, if I have this, some people say, oh, okay, I just square x and I square the 2. Yeah, that's not right. If I have a binomial technically squared, I have to write it twice and FOIL it, like this. So basically putting a 7 underneath all of these is making the exact same mistake. So what we have to do is combine this to 1 log on one side, and we can do that by going log base 7 of 2 times x minus 3, because addition means multiplication in logarithms. And now that I have log base 7 on both sides, I can now use my trick to basically get the log base 7 to be 1, and that leaves me with 5x on this side, and this leaves me with 2 times x minus 3 on this side. So if I transfer that up here, I got 5x is equal to 2x minus 6. If I subtract 2 from both sides, I get 3x equals negative 6. If I divide both sides by 3, x equals negative 2. This is the problem you need to check, because if I plug that negative 2 in for this x, I get log base 7 of negative 10. That's a problem, because I can't have this as a negative. Even in the previous problems where I had answers for negative x, when I plugged it in to the equation, it turned positive. But it isn't positive. This is log base 7 negative 10x. What if I put it here? This is log base 7 negative 5. So the answer in this problem is that there is no answer, no solution. So you should always check your answers, especially if they're negative. Now, you'll see, in problems 11 and 12 on this worksheet, yeah, they worked, but this one didn't work. Well, there it is, guys. Ladies and gentlemen, that is the end of solving for x, this video for solving for x in exponentials and logarithms. Thank you for watching.